Yeah, so it's the final talk of this session and of this week of the conference. And it's my pleasure to introduce Steven Senger from Missouri State University, who would talk on bounds on chains determined by angles. Thank you. Thank you, Steven.
Thank you for the kind introduction. Also, thank you to the organizers and especially for working me in with the odd time difference. But I got to say, this has been a really fun session. I've known everybody speaking, and so it's just like friends getting back together even over Zoom. So this has been really fun. But yeah, so I want to talk about bounds on chains determined by angles. And I'm going to start relatively slowly. This is joint work with my friends Avi Paulson and Charles Wolfe. So I want to motivate this, and you're going to hear a lot of names that you've already heard today, and it's probably going to harken back to some things we've been thinking about. But first, I use some slightly non-standard notation. So this is just how I learned asymptotics, which is a squiggly less than. So I think today most people have been using sort of less than. I'm using the squiggly less than. If ever anything is unclear, just let me know. So we've got big O and we've got big theta, just using slightly different symbols. So unit distance problem, probably my favorite thing to do, in mathematics is think about the unit distance problem. I think about this problem every day. Posed by Erdős in 1946, and the basic phrasing of the question, one way to phrase it is, if we define this quantity U2 of n, this asymptotic quantity, to be the maximum number of times that a distance can occur in a set of n points in the plane, then how big is that? And Erdős conjectured pretty famously no more than n to the 1 plus epsilon for some very small epsilon. And yet we've been stuck since 1984 at n to the 4/3. So the best we know is that no distance can occur more than n to the 4/3 times. And this is, of course, Spencer with Semerity and Trotter. And it's a sort of a similar argument to the celebrated Semerity and Trotter point line incidence theorem, because if we're counting unit distances, we're looking at incidences of points in circles. Of course, we can ask this problem in 3 dimensions. And so same question. The conjecture here is that no particular distance can occur in a large finite point set in 3 dimensions more than n to the 4/3 times. But Josh Saul has to the best of my knowledge, the best record, which is n to the 295 over 197 plus epsilon for any small epsilon. So this is a nice fraction, but I just think of it as something less than 3/2, concretely less than 3/2. And probably many of us are familiar with the length example, which says in dimensions 4 and up, without further restriction on the point sets, there can be the trivial amount, which is as many as n squared unit distances. This is trivial because there are n squared ways to choose a pair of points. Lenz's counterexample is, n over 2 points on the unit circle in the first 2 dimensions, and the rest on a circle in the next 2 dimensions. It looks like this. So if I take, I've got n over 2 points here, and I've got n over 2 points here, any choice of a point here paired with a choice of a point here will give me the same distance. So I've got, n squared copies of the same distance, and you can, of course, normalize these circles to make that distance 1. Now, this is going to be a crucial example to what comes ahead. I know the title of the talk is something about angles. We haven't seen angles yet, but this is sort of a big motivating example. And just a word to some of the previous talks from today. If we look at like the Falconer distance problem, we can think of this as a low dimensional phenomenon, which would, of course, then be ruled out in like a Falconer type problem. So if we were to consider what is this set in 4 dimensions, it's kind of a 1-dimensional set. It could be parameterized with 1 variable, as opposed to, say, like a full dimensional lattice. So that's a very rough thing, but I just want to say that it's not that it's trivial in dimensions 4 and up, but without further restrictions, this problem is trivial in dimensions 4 and up. And there are plenty of differences there. I just want to give you sort of the rough idea. So something that I have been really excited about for a while is called a chain. So a chain for distances is a set of k+1 points where we're concerned with the k distances between those k+1 points. So in this case, I've got x1, I measure the distance to x2, measure the distance to x3, x4, et cetera, et cetera, et cetera, xk and xk+1. So if I've got k+1 points, I'm measuring k distances between consecutive pairs. And I'm saying this is specifically a distance k chain because, of course, we're going to be talking about angle chains today. But if we think about the length example, it applies still for this chain thing. If I'm looking at the two circles in the lens example, I can just keep zigzagging back and forth, and I'll get roughly into the k+1 occurrences of my distance k chain. You can modify this a little bit if you don't want all the distances to be the same, but let me not dilly-dally too much there. I'm gonna just for now let c sub k of n denote the maximum number of occurrences of a distance k chain in any set of n points in the plane. And so this is just generalizing that u2. So if u2 was the number of pairs of points, that is the number of times the unit distance can occur, then this is like c1. So this is the number of times that a single distance can be determined. So with Avi Paulson, who's a co-author on this work, and Adam Scheffer, this I think 2018 is roughly when we put this out. We showed the following upper and lower bounds on distance k chains, and this was, I don't know, a year or two of work, and we did the best we could, and then some very smart people, Franklin Kupowski, came along and said, "Oh, you know, there's a better way to do this." And so if you haven't read this paper, I highly recommend it. It's a dream to read, and reading it, I'm like, oh right, this is what we should have been thinking. But it's a lovely paper, and so it's nice to read. It's well written and everything, but moreover, they basically finished the question up to the unit distance problem, at least as far as I care about chains. So I was sort of hoping that I could get a nice chains estimate, and maybe that would sort of fold back to the unit distance problem. But what Franklin Kupowski has said to me, or at least my interpretation, is that, well, that's a nice idea, Steve, but you're gonna have to work harder. So beautiful paper, lots of fun to read. But essentially this is, the buck stops here. We don't get the unit distance problem for free. Or so it would seem, without some hard work. So separately from distance chains, we have this notion of dot products, probably like just scalar inner product, so nothing fancy here. But if we ask, how often can a particular dot product occur? Well, if we're not careful and we just look at zero dot products, then we can arrange half the points on one axis, half the points on the other axis, and we have n squared zero dot products. Okay, let's look at non-zero dot products. Well, so the length example sort of squashed the distance problem in 4 dimensions. The dot products problem actually gets squashed a dimension lower. In 3 dimensions, there's what I'm going to call a length type example, which says that you can get n squared occurrences of a dot product in 3 dimensions. Moreover, you can extend this to give n to the k+1 instances of a particular dot product k chain. So this would be just like the distance k chain, but defined by dot products instead of distances, just by looking at this set here. So again, without further restrictions, this question of dot product chains sort of seems to be relatively trivial in 3 dimensions and higher. Okay, so this is all sort of motivation for what we've done in the current project, but I just want to say some other variants, at least that I'm aware of, that people have studied, and I'm sure there are many, many more. So more general configurations. So I've got a paper with several co-authors where we set up our framework for more general configurations. There are other robust frameworks as well. I recently did a project with some undergraduates looking at a mix of distances and dot products. In particular, there are some obstructions in the dot products case that come up. And one way to sort of get around those is to oscillate between distances and dot products. In fact, our morning meeting is in a couple hours to talk about this. So there are sort of peculiar things that happen, maybe not so expected, and analogous results in other settings. So sort of fairly safe settings like vector spaces over finite fields, modules over these relatively well-behaved rings. I've got a master's student who's looking at Galois rings, and that's more involved. But this is just to say that there are a bunch of variants, and you can kind of set your parameters, come up with a type of question, and you can probably prove a theorem. Okay. The thing that makes today's talk different, so this is sort of background, the thing that makes today's talk different is now we're dealing with angles, which require 3 points. And this is just a fundamentally more complicated setting. So if we fix a k-tuple of numbers that are between 0 and pi exclusive, just because I'm going to be talking about angles, then an angle k-chain is exactly what it should be. But again, since it requires 3 points to determine an angle, we're going to need a k plus 2 tuple of points to determine a k-chain. So, if I was looking at a distance chain, there's a distance, but now this does not determine an angle. So I need 3 points to determine my first angle. The next 3 points determine my next angle, and so on and so forth. This really, in some sense, what I got from studying this is that we're doing the wrong thing, that angles somehow want to be studied by using lines. And this is just my personal opinion. I don't know how much my co-authors share that opinion, but as we push forward and you'll see the different results, I got this strong feeling that, like, if we were stating this in terms of lines and not points, we would probably have some sort of like sensible results. But there are these just really peculiar things that come up when we try to state things in terms of points. So, okay, just a formal definition, and this, I know this is symbol soup. I'm just going to give you the worst of it, and then we'll sort of pull back to something readable. So I'm going to use capital lambda because it kind of looks like an angle. Capital lambda of k to denote this is the set of angle k chains determined by a set of points E with the following angles. So I had to pause and look because I never remember whether I've defined this as a set or as a number. So that's the hardest thing for me when going back and reviewing a paper is seeing if the absolute value bars are there. But this is a set. And notice here, I'm not specifying anything about the dimension because this is defined in terms of E. So if the point set E is, in a particular dimension, then that tells us where the points are. We don't have to specify it. That has advantages in the proofs because if I'm in 3 dimensions, but I'm looking at a 2-dimensional subset, I can restrict whatever. But this is a lot of symbols. So in general, I'm just going to say lambda sub k of E, and it'll probably be clear from context what lambda sub k of E means. So of course, we're not the first people to study angles. Pach and Sharif gave the following nice result in 1992. So here I'm just sort of practicing with the notation. Lambda sub 1 of E has size no more than n squared log n. That is to say, if you fix an angle and you're looking at n points in the plane, or n is some large finite number, then you can find no more than roughly n squared log n copies of a given angle. Now this is sharp for some angles, and I have forgotten which, but it's not known to be sharp for all angles. I want to say it's sharp for like rational proportions of pi or something like that. But it is sharp for more than one angle. Just it's not known to be sharp for all angles. So we just don't know. Now later, Applebaum and Sharif studied this in 3 and higher dimensions, and we'll see some more of that later. But in 3 dimensions, they showed that there were no more than n to the 7/3 triples of points determining a fixed angle. And this is sharp for pi over 2, so it's sharp for right angles, but it's not known to be sharp for all angles. And the construction here is the construction they give is essentially a 3-dimensional lattice, and you're looking at the incidences of spheres and lattice points. So it's got a really sort of Erdős distance problem flavor. It's got a really sort of classical number theory flavor. Anyway, so the results that we got, and in 2 dimensions, it's relatively tame. What we got is essentially what you would expect if you apply the original Poch and Sharif. So if we have an even, if k is even, then we can play the following little game. So here's x1, here's x2, and like I said, x1 and x2 are going to uniquely determine a line in 2 dimensions. Well, I mean, they'll always uniquely determine a line, but here we're in 2 dimensions. And then if I pick x4, this choice of x1, x2, and x4 essentially uniquely determines where x3 can be so that I can get the angles that I want, alpha 1 and alpha 2. So for k even, when we have a pair of angles, we can sort of Lego brick these things together. Once, if I was looking at 4 chains, I've got x1, x2, x3, x4 chosen here. Then I can choose x5, and the choice, since x3 has been sort of fixed for us and x4 has been chosen for us, if I choose x6, that'll fix x5, etc. So it's a fairly straightforward bootstrapping. And just if we need to use Poch Sharif, that is, if k is odd, then we'll use a Poch Sharif somewhere in there. So fairly straightforward. Not exactly rocket science. This is sharp up to logs, basically sharp up to this log. And the construction is what we call sort of a crooked railroad. You have something like this and something like this. And then you can set these lines at whichever angle so that you get the angles you want that pop out. It's pretty straightforward, not that bad. So you got the angle you want. Let's say you start here, you get the angle you want here, you get the angle you want there, angle, and you can just sort of do this. So 2 dimensions was fairly straightforward for us. Oh, sorry, I guess I'm going to explicitly state what I just sort of sketched out. There exists a set of points that has this n to the floor k over 2 plus 2 angle k chains of a given type. Okay. 3 dimensions. So we started studying this maybe 2 years ago. Within a few weeks, we had 2 dimensions in our, as much as we wanted it, we had pretty much licked. We're happy with 2 dimensions. And so we said, well, let's move on to 3 dimensions. In 3 dimensions, immediately was very, very difficult. So we spent, like I said, it was about a 2-year-long project before we submitted our paper. About 1.5 years of that 2 years was spent just looking at the case of 2 chains in 3 dimensions. Right angle 2 chains in 3 dimensions specifically. So what is a right angle 2 chain in 3 dimensions? Well, now we're in 3 dimensions, and we're looking for 4 points where this is a right angle and this is a right angle, and that's it. Now the issue is, it can spin around. So there's some additional movement that's possible here. And we have a whole bunch of partial results. We have pages of partial results, and we kept thinking, okay, if we stack all these cases together, then do we get it? And there's still some subcase that slips out. So then if we address that subcase, then we have to arrange the cases differently, and it always seems to fall out to where we don't quite have the 2 chains. So eventually we said, let's just push out what we've got. But it would stand to reason that the number of 2 chains can be no more in 3 dimensions, can be no more than n cubed, but we could not prove it. We couldn't rigorously show that without making additional assumptions. So we only proved the so-called trivial bound. And this is a trivial bound because it's essentially a direct corollary of Applebaum and Sharif. Applebaum and Sharif tell us, well, we have no more than n to the 7/3 triples of points determining a fixed angle. And now we're saying, well, and you've got no more than n choices for that 4th point. I mean, this is horrible. But in 1.5 years, this is all we could get. So if you have any interest in this, please, you're welcome to it. However, for longer chains, we did manage to get some non-trivial results, and this was quite fun. So for 3 chains, we got an upper bound of n to the 4th. Again, we're restricting to right angles here. For 4 chains, we got into the 13/3. For 5 chains, we got into the 5th, and then we just derived a recurrence based on sort of this initial data. You just do it like a undergraduate ODEs class, and it's still got this sort of thorn here. So if we could improve this, then we believe that this would improve, at least for certain cases. But essentially, we couldn't quite take advantage of, for the 2-chain case, we couldn't take advantage of what we could in the later cases, which is we could split into cases based on coplanarity. So if I have, these 3 points that are in a plane, if a 4th point is in a plane with them, then I can reduce down to the lower dimensional cases. If the 4th point is not in the same plane as those first 3, then I have a different set of tools. So it was like I said, it was a really enjoyable pursuit, going through these things, going through these pieces, but this was just really challenging for us. So I just don't know what to do in the case of that is quadruples of points that determine 2 right angles in 3 dimensions. This is our white whale. Okay, we have some constructions, some lower bounds, and I want you to think, I mean, you can think however you want, but I kind of think of it as very Lentz type. The Lentz example, basically I think of the Erdős lattice counterexample, and I think of the Lentz type examples as sort of 2 big counterexamples for any problem that I look at. So Appelbaum and Sharif came up with a set of n points in R4 forming n cubed right angles, and if memory serves, it's somehow points arranged on a circle. I actually just pulled it up, and I just pulled it up so that I wouldn't be lying to you. But it's essentially cleverly arranging points on circles in such a way that you get right angles. Then we managed to show that you can take basically the same idea, which is, again, lower dimensional phenomena. There's a set of n points in R5 forming n to the 4th right angle 2 chains. Oh yeah, R5. I got really scared for a second. Yeah. And then in R6, that's when it kind of trivializes. There's okay, this is what I had pulled up. There's a way to set up sort of points arranged on 3 circles, kind of, in some sense, in 6 dimensions. And then you can just sort of go around and you can pick a point off of each sort of, there's a cycle of 6 points, then you can just go as long as you'd like. So once we get to 6 dimensions, this problem is really kind of trivial the way that we see it. And this would correspond to the Lentz type example in that, for 2 points, we needed 2 copies of R2. And for 3 points, because these are angles, we need 3 copies of R2 in some sense. This last result is actually, it's going to hold for more general angles. It's not just right angles. We didn't fully classify which angles it worked for, but there's just sort of, by the nature of how the example works out, you can sort of fudge a little bit and get more general angles. But that is just to say that the problem seems to peter out in dimension 6 without further restrictions. So the last thing that I wanted to mention, as the title of the talk indicated, is some pinned variants. And again, this harkens back to sort of the main theme of these angles, is they're fundamentally different than a lot of other things that I've studied, these Erdős type discrete geometric combinatorial problems, because the point that you pin really matters. So if I'm pinning the middle point, so if I'm pinning the middle points of my angles, it's pretty easy for me to just have that angle occur n squared times. I throw n points on this line, n points on that line, and make sure there's a point here. And then I've got n squared copies of that pinned angle with the middle point pinned. However, if instead of pinning the middle point, we pin the first point, which might be more natural. That's how a lot of pinned things that I've seen in the literature go, is you pin the first point and check what follows. In that case, we can show that there are at most n to the 4/3 pinned angles, again, by pinning the first point, pinning the first or the third point. And this is sharp. And the sharp construction is based on the sharpness construction for the Semirati-Trotter point line incidence theorem. So what's happening here? Pinning X1 can be very different from pinning X2. And again, maybe we should really be studying lines instead of studying points. So pinning the first line or pinning the second line or you know, ray, however you want to think about it. So again, more just explicit results on pinned points. We can construct a set of endpoints in R3 with n squared right angles starting at the origin. We can also modify this is just a selection of the results. We have a paper on arXiv with a lot of different sort of results filling in the gaps here. In R6, pinned or not, it's sort of done. You get the trivial amount of k chains, because if you've pinned the first point, then there'd be n to the k plus 1 other choices for the k plus 1 further points. And again, this last result, because it's a variant of the previous one that I mentioned in R6, it does hold for some pardon me, for some more general angles. And then just a word, I had planned to, I know this is a session on additive combinatorics. I had actually planned to get some additive combinatorial results using these theorems. And I started to write down what I would get, and they were so the estimates were so bad that I stopped writing. So you don't get any explicit additive combinatorics out of this. I looked at sort of, you know, thinking about the angle as a relating it to a dot product, and it just, the results were not interesting enough to write down. So I really had hoped to relate this more directly back to additive combinatorics, but when I looked at it, I couldn't find anything particularly interesting. Anyway, that is just to say, thank you so much for your time and for your kind attention. This has been a really fun session for me to watch, so I appreciate all of you being here.
Thanks a lot, Steven, for a very interesting talk. I have a couple of questions, but maybe someone else has also some questions. Yeah, and by the way, thanks a lot for your kind words about our paper. I'm happy that you liked it. So one question, yeah, one question that I had is about conditions on distances or on angles in this case, when you would actually get bounds that are like upper bounds that would be worse than the bounds for the best angles. So this kind of, do you have any kind of results of that form? Because for the chains, I don't think it's possible, or at least in higher dimensions. I think you can like do it for any set of distances, really. But for the angles, do you have anything like anything?
That's a
explicit?
totally fair question. No, I don't. In a short word, no. I think the issue is we know that, so that the worst cases are these sort of number theoretical things. That or I shouldn't even say worst case. The cases where we know what's tight come from, like I said, a lattice, and you can just explicitly compute what you're going to get. Or these silly low dimensional things where you just follow your nose. So some of those can be adapted to general angles, but like the lattice example works because, you know, when you have a sphere here, if you've got 2 points on the sphere, then you know how they're going to interact, how they're going to define an angle. Whereas with so we looked at non-right angles, and instead of the intersection, I guess this is kind of a horrible picture. Instead of the intersection of like what would be a plane and a sphere, we're going to be intersecting like a cone and a sphere, and it just gets really nasty, and we couldn't figure it out. So that's not to say that it couldn't be done, but yeah, we gave up real quick. If I answered, I might have dodged your question really efficiently, but
no, I got. I mean, I understand that. So what we were trying at some point to think about is, so with Nora we worked with also. We are about to put out a paper on simplices. There is this Agarwal-Sharif conjecture, also Erdős and Purdy conjecture, and there you maximize the number of simplices on the points set, so which is a much more rigid configuration. And I was thinking about like, okay, you get this general bounds from some kind of cutting results, but like there, since the structure is very rigid, it clearly depends on the distances that you impose, and even if simplices exist with given distances, maybe the bounds can be much better for a particular types of simplices. So yeah, I was wondering, like here the situation is much looser, but because yeah, less restrictions. I was still like wondering for the chains. I don't think it doesn't. I don't think it makes any difference. Like what distances do you put here? Yeah, I was wondering if it makes, but it's difficult to pin. Unfortunately, for the simplices, it's difficult to pin. Maybe here as well.
Yeah, and now that you say the word simplices, I'm sort of embarrassed I didn't mention simplices or like the star configurations specifically, but those have been very widely studied. And yeah, I remember there was something that my advisor did with one of his graduate students that was about almost rigidness. So when you had like a countable number of ways to redo something. So if you had like if I had part of a distance set, let's say I've got a 4-point configuration, and I have part of the distance set. Let's say I've prescribed these distances, but I have not prescribed that distance. Then you don't have a range of movement, but instead you've got a countable number of potential configurations. And I can't. They had a very straightforward name for it and a very straightforward way of dealing with this, and they proved some theorems, and I don't remember what it was. I could email you if you'd like. Because maybe
that sounds very interesting.
Yeah, I could definitely email you that. It's called like almost rigid or really rigid. I can't remember. Sure.
Great. Yeah, I also wanted to mention that we were for a while we were like being stuck with trees in the first setting. We were thinking quite a lot about trees, but it seems to be very hard. Like for some classes of tree. I think you did you write also something about that, right?
Yeah. So Avi's master's student. This is a horrible tragedy. He worked very hard, like very, very hard, and proved some nice results on trees. And then Avi, within a week or two before he defended his master's thesis, Avi pointed out that, if you specified the children on this layer, then they determine the whole tree up to a constant number of variants. So we have a preprint on archive, and it's going to be in like a conference proceedings. But essentially, this was Ben Rhodes was the guy who did all the trees work. We proved theorems around in such a way that his trees work was not in vain. So it's something like it was like binary trees and or ternary trees and in 4 dimensions. There's some way to do it, but yes, you're right. Unless you're in a trivial case, it gets absolutely just blood on the walls. It's horrible. But yeah, it's like you either have a trivial setting, or as soon as you open the gate, it just everything goes all over the place. So yeah, surprisingly difficult.
Yeah. At some point we were ambitious and we're thinking, okay, so we did the path, then we just solved the trees, and it doesn't seem to be working that way. Yeah.
Yeah.
I think we got something non-trivial, like some new ideas in addition to what we did in the paper, but really not much more. But yeah, I hope we'll put it out soon at some point.
Yeah, I saw it because I remember the first version of your paper, and then the second version of your paper had the richer graphs on the end. Yeah.
Yeah. But these angles, yeah, that's an interesting thing. We're also at some point Nora was suggesting to look at it. We just have a big backlog of things we had to write down. So I thought, okay, Nora.
Well, it's really
it's an interesting work. Very interesting.
Thank you. Yeah, it's the 2 chains in 3 dimensions. That was a year and a half.
Yeah, it looks like a very good.
It's so hard. We have no idea.
Looks like a great question.
Oh. Well, yeah, I'll send you an email with this thing, and it was nice to meet you.
Yeah. I'm happy to meet you too, and yeah, thanks a lot for sharing all these nice questions and nice results.
Oh, thank you, and thanks again, Tong, for reaching out and being so kind with the time difference and everything. I appreciate that.
Thank you very much for giving the talk.
Yeah, sure.
Yeah, and thanks, Tang, for organizing this.
My pleasure.
This workshop. Great. Okay. Bye, everybody.